Welcome to the deep dive. Okay, if you've got an ATPL theory exam breathing down your neck, you'll know exactly why we're zeroing in on this topic today. We are tackling an instrument that's, well, it's mandatory, always there, but also, let's be honest, fundamentally flawed. The direct indicating magnetic compass, the DIMC.
It really is a paradox, isn't it? It's your ultimate backup, the thing you rely on when the fancy glass cockpit goes dark.
Right.
But at the same time, its whole operation depends on this really weak magnetic component that gets distorted all the time. So, it's practically designed to show errors when you maneuver.
That's exactly it. And that's our mission today. We've got a whole load of source material here focusing on how this thing works, its requirements, but crucially, the dynamic errors.
Ah, yes, acceleration and turning errors. The examiners love these.
They really do. So we're not just listing facts. We want to really get inside the why. Understand the forces that cause those errors. That's the key to nailing those ATPL questions, moving beyond just memorizing rules.
Absolutely. You need to grasp why the compass reads what it does in a turn or during acceleration, not just what it reads. Okay, so let's set the scene. What's the compass trying to do?
Fundamentally.
Fundamentally, it's trying to point your heading relative to the local magnetic meridian. And that meridian is dictated by the horizontal slice of the Earth's magnetic field, the H component.
Okay, H component. And straight away, we hit two big sources of, well, we call them navigational inaccuracies we always deal with. First, there's the geographical one.
Magnetic variation, yeah. The angle difference between true north geographic north and where the magnetic field lines actually point at your location, that's just a fact of geography.
Right, fixed for a location.
Yeah.
But then there's the aircraft itself causing problems.
Compass deviation. This is the local issue. The angle caused by all the magnetic bits and pieces in the aircraft, the iron, the steel, the engines, especially electrical currents.
Yeah, wiring looms.
Exactly. All that stuff bends the local H field so the compass magnets don't quite align with the actual magnetic meridian anymore. They point somewhere else.
Got it. Variation is geography. Deviation is the aircraft messing things up locally. Okay, let's dive into the engineering challenge. How do you even make this thing work reliably?
Well, we're mostly talking about the direct indicating magnetic compass, the classic type. You look right at it.
The one you see in, like, Cessnas and Pipers?
Often, yes. The vertical card compass, sometimes called a B-type or E-type, that's usually the main one in lighter aircraft, or it's the mandatory standby compass in bigger jets.
Right, the backup. So, structure-wise, it seems simple enough. Magnets, a card, liquid in a bowl.
On the surface, yeah. A circular card attached to the magnet assembly floating in liquid, read against a lubber line. But the real cleverness and the source of all the problems later isn't how it's suspended.
Because the aircraft's moving all over the place,
Yeah.
pitching, rolling.
Precisely. Keeping that magnet assembly pointing roughly north while the aircraft does its thing, that's the challenge. And it boils down to three absolute must-haves for the magnet system. Exam critical points, these three.
Okay, let's hit them. Number one, and you hinted this is the big one for errors, horizontality.
Horizontality. The magnets have to lie as close to the horizontal plane as possible. Because heading, direction, that's measured horizontally, right? Azimuth.
Makes sense.
But the Earth's magnetic field isn't horizontal except right at the magnetic equator. Everywhere else, there's a massive vertical pull.
The vertical component Z, trying to pull the north end down in the northern hemisphere or up in the southern.
Exactly. So if the magnet was totally free, it would just dip down massively. Useless for direction.
So how do they stop it just pointing at the floor?
Clever trick. Pendulous suspension. They deliberately design it so the center of gravity, the CG of the whole magnet and card assembly, is slightly lower than the pivot point it hangs from.
Like a pendulum.
Pretty much. So when the magnetic Z component tries to pull the magnet end down, the dip, the weight acting through that low CG creates an opposing force, a righting couple trying to level it out.
So gravity fights magnetism.
In effect, yes. The system finds a balance point where the dipping force from Z is counteracted by the stabilizing force from the weight and the offset.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best